Okay, so the menu for today, a few things I'm going to try and cover in this kind of short period of time. So I'm going to hop through various aspects of the glacial system. I'm going to give you a quick introduction on glaciers. I'm sure a lot of you are aware of these, given the background that I'm told many of you are from. But it's going to be a quick glacial 101, a quick introduction on glacial biogeochemistry, and also kind of like an overview of why I think the Greenland Ice Sheet is particularly important in this story. I'm going to talk to you about nitrogen on the Greenland Ice Sheet surface mainly. I'm going to talk to you about phosphorus, which behaves slightly differently to nitrogen in terms of the glacial system. And then I'm going to finish with arguably my favorite element, iron, and talk to you about why ice sheets could be potentially important in global iron cycling, or at least regional iron cycling. And the red thread kind of putting all this together is the mobilization cycling of elements from the ice sheet and particularly from underneath the ice sheet to downstream ecosystems. Okay, so I'm going to start, and this GIF is really a nice excuse to talk about one of the great issues of our time. How much carbon we're injecting into our atmosphere from the burning of fossil fuels, land use change, and the impact that's having on our climate. The CO2 levels have not been this high since the Pliocene, millions of years ago. 2023 was the hottest year on record, and this is fundamentally changing the world in which we live. And the impacts of this climate warming are perhaps no more obvious than the polar regions, where temperatures are rising faster than pretty much anywhere else on Earth, twice the rate of the global mean, twice, 3 times the rate of the global mean. And in these regions, we obviously have the bulk of the cryosphere, which is extremely vulnerable to these changes in temperature. And we all know this. Ice is melting at an increasingly rapid rate, and this is leading to sea level rise in the order of millimeters per year. Most of the past sea level rise from the cryospheres come from these things that I've classified as other glaciers, the very important mountain glaciers mainly. These are driving a lot of the sea level rise until about the last 10 years or so, 10, 15 years. And now we're seeing a lot of the sea level rise from the cryosphere coming from the Greenland Ice Sheet and a little bit from the Antarctic Ice Sheet as well. So there's a lot of water, a lot of fresh water.
Really quick, John, I just want to interrupt you. We're also seeing the first slide.
Oh, okay.
I don't know if you want to try resharing.
Let me try resharing this then. Okay. Can you see this? No?
Yeah, could you maybe just try changing slides just to see if that goes through?
Can you see any change in slides?
No, it's still the same. Is anybody else seeing changing slides? Is it just me?
No.
Oh,
Is it because the multiple screen thing?
Hey, Cassie, I can see it. It's not a problem now for me. What does
You
this
can
mean
see
for the world's ice? Yeah, I can see it.
Well, so I see the newest slide, but are you able to see? So he's saying that he's playing this slideshow and now changing the slides. Are you changing them?
I'm changing the slides now. Can anyone see these changing slides?
So it's just, for me, it's just staying on what does this mean for the world's ice? Is it saying?
Yeah,
we have
page slide 4. Slide 4.
Oh.
Yeah, switch to like 3 or 5 or 2.
Okay, yeah, I see the menu slide now.
Okay, me too.
Okay.
Me too.
Okay, I don't know what's okay. Can you see that now?
Yes,
Yeah, okay, things are happening.
Okay, I'm really sorry about that. I don't know what happened there. Very odd. It seemed to work when we were testing it earlier, but for some reason not now. Okay, well, there's my introduction. Hopefully you heard me voice it over anyway. But that's the menu for today. And then this is just the nice little GIF that you missed of global temperature rise since the kind of pre-industrial period. And I think I was just highlighting here how temperatures are rising most rapidly in the high latitudes, particularly areas where there's the bulk of the cryosphere. So this is this is leading to sea level rise. And I'll skip over this slide quickly, but sea level rise and large fluxes of fresh water coming from ice into the ocean or into downstream systems. But there's kind of another story that I'm interested in here, and that's glaciers in the past as well, and during these kind of glacial interglacial cycles as they wax and wane their way over the continents. And this is just an example of what ice looked like during the last glacial maximum, over much of North America, pretty much down to where I am now in Philadelphia, but also over large parts of Europe as well. And there's all kinds of interesting things that we're starting to find out about these paleo ice sheets. I've thrown in this figure here just to show you underneath the North Sea, all these old subglacial channels that are being discovered and mapped, indicating like a connection between ice sheet surfaces and their beds going back to 21,000 years ago, and not something that we're just observing now in places like Greenland. So we know very little about these environments in terms of biogeochemistry, and that's why largely they've been left as these kind of blank spots on maps of budgets when it comes to dissolved solids in this case, but write any element you want or any nutrient you want, and they're kind of blank spots still. And same comes for things like fluvial sediment discharge into the oceans. And we now know in the last 10 years or so, less than that, last 5 years, that the Greenland Ice Sheet in particular could be responsible for a huge amount of sediment input into the coastal ocean, from just 1% of land surface area that it covers, or just under 1% land surface area it covers. It could be responsible for 7, 8, 9% of global sediment export from rivers to the ocean. So within that respect, anyway, we're making large bounds in our understanding. So the old view, particularly from the paleo community, and this is I'm not trying to insult the paleo community at all here. It's a very reasonable views to have, really. Was that during interglacials, chemical weathering in particular was higher because it's warmer, it's wetter, it leads to more chemical weathering, higher inputs of things like nutrients potentially into ocean areas. Faster rates of chemical weathering on catchments that could also have implications for carbon dioxide drawdown. And then basically, if you put ice over land, you slow down this weathering. And, with a lot of the kind of old models and, old traditional viewpoints of these systems, you put an ice sheet or a glacier over a land area and you shut off weathering altogether. Nothing happens. It's basically a zero flux to the ocean, or zero flux downstream. Doesn't have an impact in terms of chemical weathering or biogeochemistry. What we know now is that the beds of ice, beds of glaciers, beds of ice sheets, there's actually this amazing unseen wetland, hidden wetland. And I'm just showing you examples here of Greenland Ice Sheet and the Antarctic Ice Sheet. Our understanding of the hydrology underneath these ice masses has really changed considerably in the last 20 years. We now know that there's a lot of liquid water underneath the Greenland Ice Sheet, and almost everywhere we look underneath the Greenland Ice Sheet, we seem to be finding liquid water that has all kinds of interesting geochemical compositions. With the Antarctic Ice Sheet, we've identified nearly 700 subglacial lakes now. So these are lakes that exist at the ice rock interface underneath the ice sheet under kilometers of ice. And we've actually drilled into 2 of these subglacial lakes to get samples for geochemistry and microbiology, and to try and get some kind of understanding of Antarctic ice sheet dynamics. That's Mercer Subglacial Lake and Willen Subglacial Lake here. And these lakes are actually, some of them are connected and drain and fill and cycles. Some of them are what we call isolated, that seem to be hydrologically isolated from other water bodies under the ice, and so could have been there in their present form for tens of thousands, if not hundreds of thousands of years. And there's also evidence in Antarctica of these subglacial meltwater channels funneling water from the ice sheet interior to the margins where ice meets the ocean. So here's my very quick Glacial Hydrology 101. This is a schematic I adapted from Chu in 2014. This is pretty much what a Greenland ice sheet catchment looks like if you cut it open, or our conceptual idea of what it looks like. This is it probably kind of midsummer, when we've removed a lot of the snow and fern from the glacier surface that was deposited over the winter period. we have some surface melting going on. So we have some supraglacial lakes, these lakes that form on the surface of the ice sheet, can be, several kilometers in diameter, and these guys can drain extremely rapidly through the ice sheet to the subglacial environment. Over a kilometer thick of ice, they can drain very rapidly. Things like crevasses, ponded crevasses, open crevasses, and moulins, these kind of pipes in the ice connecting the surface to the bed. And here we are. This is very characteristic of surface meltwater. Very clear, stuff that you'd quite like to drink if it weren't so dilute and cold. But funneling large quantities of water from that ice sheet surface in the summer to the bed, where we have this subglacial system. We have very high rock-water ratios. We have all kinds of interesting geochemistry occurring. This is just some pictures from the bottom of an ice core that was retrieved. It was liquid water that flooded into the bottom of an ice core from Greenland and refroze. And it's this kind of like stained color here, this kind of rusty color. And then this water is funneled through this subglacial hydrological system, which is constantly changing as well, changes very dramatically from initial melt in the early summer to peak melt, as I'll show you in a minute, and emerges from the glacier as this large river, very, very sediment rich. That's why it's kind of this murky color, very characteristic of Greenland ice sheet meltwaters. And this is what it looks in terms of a video to give you some better perspective. So this is probably kind of early, mid-June, this river that we often go to and study that I'll be talking about for the rest of this talk. This is probably in July time. So kind of very dramatic. This is a waterfall here that you're seeing, and some rhodamine dye injections that we're doing. And then we're going to get, here we are, mid-July. And then we're ramping up into peak melt, where this one river draining from the Greenland ice sheet margin is, 2 to 3 times the size of the Delaware River in terms of discharge. So huge river. From a trickle in May to twice the discharge of the Delaware River in July. And then these land terminating glaciers, where the ice terminates on land, meet the ocean and create these very dramatic, in some instances, sediment plumes that you can see from space, all that sediment that's carried in the meltwater being discharged into that ocean there. And then we have these marine terminating glaciers that we know very little about in terms of hydrology, although we just assume that they're kind of similar to land terminating glaciers in terms of hydrology, that they just discharge into the ocean. And this has kind of dramatic implications for the hydrodynamics of the coastal environment, and actually really, really big implications biogeochemically. And I'm not really going to talk about that today. But here we have our moulin draining into our subglacial channels in this particular video, and emerging the front of the glacier as these buoyant meltwater plumes. And what this does actually biogeochemically is entrains deep oceanic nutrients and brings them to the surface. So really, really important for ocean ecosystems, these types of glaciers. And this is my very basic introduction to glacial biogeochemistry, or glacial geochemical weathering, and why I think it's so interesting. So here's my cartoon of a glacier flowing over bedrock. What these guys are is they're like big natural bulldozers. As they're flowing over the bedrock, they're crushing and grinding that bedrock, abrading it. And they're basically taking solid rock and bashing it up into all these micro nanoparticles. So any trace reactive components in this bedrock go from being locked away to suddenly being exposed to very fresh, very dilute meltwater that's coming in from the glacier surface. And we get all kinds of very rapid chemical weathering reactions that go on here. And we get formation of nanoparticles, we get transport of nanoparticles, and throw into that as well some microbes that help catalyze some of this chemical weathering reactions, some extremophile microbes, and you get a very interesting environment biogeochemically. So we have this quite complicated actually system where we have water coming from a few different places. We have water stored at the bed for long periods of time, maybe a year or maybe even more than a year in some instances, that has high dissolved solids, long residence times, a lot of evidence now of potential anoxia in certain regions of the subglacial environment. We have methane, for example, emerging from the margins of the Greenland Ice Sheet, quite high concentrations of methane in some instances. And we also have this kind of opposite side, which is this surface meltwater that I showed you a picture of in one of the initial slides. It has very low dissolved solids, no sediment in there whatsoever, very short residence times, and kind of super saturated with oxygen because it's coming from the surface and draining through these moulins. And then we have some stuff in between, like basal meltwater coming from the base of the ice sheet that's melting. And then throw in these kind of freshly ground sediments, these physical erosion products. And then we sample the water at the front, and we kind of have to try and make an assumption about where that water might be coming from and the pathways it's taken. Particularly as these systems change so much over a melt season, it's really important to get temporal samples of these systems to really understand how each of these components of the glacier is mixing and producing what we're observing at the front. So I'm focusing on 3 elements really for the rest of this talk. It's kind of like almost a greatest hits of stuff that I've done and stuff that other people have done in the past, but it's also 3 elements that behave quite differently, I think, from a glacier biogeochemistry perspective. It's nitrogen and phosphorus, those big macronutrients that a lot of people know, a lot of biogeochemists are interested in and know a lot about, and this micronutrient iron, which is very interesting in a glacial perspective, in a Greenland Ice Sheet perspective, as I'll get to later in the talk. And these are important biological elements. Biomass of living things contains, around 30 elements, give or take a few. And all organisms have to obtain some kind of chemical form of these elements from the external environment to grow, to survive. Some in very small concentrations like iron, some in relatively large concentrations like nitrogen and phosphorus. Like the subglacial hydrology, we're making it even more complicated. There's lots of ways you can get the products of glacial weathering, chemical and physical weathering, to the ocean and potentially to ecosystems in the ocean, or at least downstream ecosystems. There's direct ways, so meltwater, what I've been talking about, these large rivers that exit the Greenland Ice Sheet, icebergs that can carry iceberg rafted debris, but also stuff that's dissolved or retained within the ice matrix. And then there's these indirect ways of getting nutrients to surface ecosystems in these coastal environments. And one of those is that kind of ocean water entrainment that I talked a little bit about, and why marine terminating glaciers are so important. So that fresh water coming in and forming this buoyant plume that draws up deep oceanic nutrients to the surface of the coastal system. And there's also this other mechanism, which is benthic recycling. So stuff basically coming from the sediments in fjords, in coastal environments, after you deposit all this freshly kind of ground up reactive subglacial bedrock, and you have some reprocessing or additional processing that occurs in the fjords. To make things simple, I'm just going to talk about this. I'm not going to get too much into, indirect nutrient fluxes or the importance of indirect versus direct. I'm just going to keep it simple and talk about what I know most about. So here we are. The mighty Greenland Ice Sheet covers around 20% of land surface in the Arctic, exports about 1,000 kilometers cubed of fresh water to the coastal oceans every year. As I've said, it exports a huge amount of sediment. Could be 7, 8, 9% of all sediment discharge from rivers to the ocean, despite just covering 1% of land surface area. And so it's really an interesting place to go and do work. Kind of regionally important fluxes of these things, sediment and fresh water, to coastal systems. And I've just given you some example comparisons there from some of the major Arctic rivers. And most of our work, or most of the work that I did when I was a grad student and postdoc, was based at this glacier called Leverett Glacier on the western margin of the Greenland Ice Sheet. Here's a boundary of its approximate catchment area. It's very difficult delineating these catchment areas in Greenland because, it's not very obvious from the surface of the ice sheet where these catchments fall, but this is where we think the Leverett catchment is anyway, about 600 to 900 kilometers squared, so there's uncertainty there. Goes to about 50, 60 kilometers inland from the ice sheet margin. about 2 kilometers cubed of fresh water per year is just coming from this one small, relatively small catchment on the western margin of Greenland. I'm sorry about this dodgy camera work down here as well. And it has a suspended sediment load of about 1 gram per litre-ish, plus or minus 0.5 grams per litre. So we think this is a good area to go to because we think it's fairly representative of the glaciers on the western margin or the southwestern margin of the ice sheet anyway. And this is what the hydrology looks like for anyone out there who's into discharge hydrographs. This is over 4 years where we had very high resolution monitoring of this river. And again, there's that river down there in the bottom right-hand corner that I showed you earlier. You can see this incredible change in freshwater flux from this one catchment over the course of, from May to September time, October time, goes from being a little trickle to a river that's, twice the size of the Delaware, back to being a little trickle on the space of 100 days almost. This is electrical conductivity on the right. This is just a kind of an idea of how much stuff is dissolved in the meltwater. And I really want you to take away from this that it starts high generally and it goes low. But so discharge goes up, and electrical conductivity, so total dissolved solute, generally goes down, but there's some blips, there's some diurnal cycles, you can see these ups and downs. And this is all related to these changes in that subglacial hydrological system and where the water is coming from. So in terms of like bulk geochemistry, I just wanted to put this figure on here just to give you some idea already that these areas, these glaciers, these ice sheet catchments actually can chemically erode quite significant loads of cations. So on this top left-hand corner here, we have tons per kilometer squared, the yield of this total cation yield. And this is annual specific discharge. And actually, a lot of these Greenland ice sheet catchments in Greenland have a similar yield in terms of cationic flux to some of the major rivers around the world. So these are not systems that are just like frozen to the bed, that have no implications for chemical weathering. These are systems that can actually produce yields of some of these cations that are similar to some of the major river basins around the world. So I just wanted to give you that as kind of some initial context and where we're coming from. Okay, so surface sources of nitrogen. I've given it away already why I think this is kind of interesting. So the global nitrogen cycle, central to biogeochemistry of the Earth. It's one of the most important elements for life. Large natural flows of nitrogen usually come from the atmosphere into terrestrial and marine ecosystems, largely by biological nitrogen fixation, in which that kind of unreactive molecular nitrogen, N2, is reduced to ammonium compounds from nitrogen fixation. Nitrogen's used in lots of cellular functions. I'm not a microbiologist, so I'm not going to get into hot water here by giving you exactly what functions, but things like amino acids, proteins, nucleic acids, other cellular components such as chlorophyll have some nitrogen in. And it's thought to be one of the key limiting nutrients in the oceans around Greenland as well, nitrogen. So this is a little story of a publication we put out there in 2016. Primary author was Gemma Wadham on this one, of some work that we did looking at surface to proglacial connections in terms of the nitrogen cycle. So roughly what we did here is we had a supraglacial sampling site. So this poor guy here, Dave Chandler, what hero in my eyes, decided to camp on the ice sheet for 3 months. He was doing another project, so this was a side project for him, taking samples of surface meltwater, cryoconite holes, and at the same time, we were camped down here in front of the ice sheet at that Leverett Glacier that I've been talking about. Actually, it's this one here, taking samples from this proglacial river. So what we see here is kind of Leverett Glacier demonstrates a continuous supply of nitrogen in meltwaters, but dissolved in organic nitrogen concentrations. This is a combination of nitrate, nitrite, and ammonia, are pretty low, from 5 micromolar in that early season melt when the river's quite small, down to less than 1 micromolar when that river really is ramping up and quite large. We have dissolved organic nitrogen in the meltwater as well. which has a similar concentration to dissolved inorganic nitrogen. So slightly higher in the early season, or slightly higher in the early season, maybe around 5. In the late season, similar to dissolved inorganic nitrogen, around 1 micromolar. But these are relatively low concentrations. And most of this nitrogen seems to be sourced from the surface, maybe from atmospheric deposition, maybe from microbial processes occurring on the surface, so biological nitrogen fixation, taking in some of that atmospheric N2, converting it to something useful. But there does appear to be a subglacial nitrogen source, and that's really the power of sampling on the surface and in front of the ice at the same time. This is total dissolved nitrogen in this case. But you can see an intercept here of around 2 micromolar, where the moulin, so that's the stuff going into the ice sheet, into the subglacial environment, is below detection in terms of total nitrogen. But out front, where we're sampling that proglacial river, we still have about 2 micromolar of nitrogen present. So there does seem to be a subglacial source, even though most of the nitrogen is probably coming from the surface. An interesting thing for us as well is that, you know, more than 50% of the nitrogen seems to be from the surface, but also more than 50% of the nitrogen seems to be organic nitrogen, which we knew very little about before this study. And if you wave your arms around a little bit and you try and come up with a similar order of magnitude to other locations, the total export from the ice sheet based on this data, based on discharge weighted means, I should say, is a similar order of magnitude to that of an Arctic river, about 40 gigograms per year. But we're still pretty low in terms of nitrogen concentrations compared to a typical Arctic river. So typical Arctic rivers, maybe 3 micromolar of dissolved inorganic nitrogen, quite a lot of dissolved organic nitrogen, about 12 micromolar. And we're down here kind of at least half the amount of nitrogen in these rivers. So ice sheets, not a big source of nitrogen, but still, you know, still a consistent source of nitrogen. And still a lot of these concentrations would be higher than what you might observe in fjord environments, if only a little bit higher. Gets very interesting though when you just look at the surface of the ice sheet. This isn't my data, I should say, or data that I was involved with. This is from Alex Holland. She was looking at this dark ice on the surface of the Greenland Ice Sheet. So low, medium, high amounts of impurities in the ice she was sampling. And she actually saw like very, very high concentrations of dissolved organic nitrogen retained on the ice sheet surface, on this kind of living crust of the ice sheet. And really, really high, you know, up to 15 micromolar of organic nitrogen, so similar to Arctic rivers. But interestingly, she also sampled these surface rivers going to the moulins, and those concentrations are as low as we were observing as well in our study. So these ice sheet surfaces, biologically productive, living skins, cycling a lot of nitrogen seemingly in these ice ecosystems, but very little of that nitrogen is getting into the ice sheet interior and being exported from the ice sheet into coastal environments. So there's a surface weathering crust. Ecosystems produce high concentrations of organic nitrogen, but that nitrogen seems to be retained in the superglacial environment rather than exported into the ice sheet interior subglacial environment. And I just wanted to put this in there because I think it's really cool. These are some sensors that some colleagues of ours were working on from the National Oceanography Centre in the UK. This is Alex Beeden, who is the mastermind of this nitrate sensor. He's now working for a spin-off company called Clearwater Sensors. And we deployed one of these nitrate sensors into the proglacial river of Leverett Glacier. You'll see it here. And these sensors read off nitrate concentrations every 15 minutes to half an hour. So you can get really high resolution records of nitrogen species in river waters and start to see these very interesting kind of diurnal cycles in nitrogen, or in nitrate in this case, that you wouldn't otherwise be able to see just by doing spot sampling, even if that spot sampling was at quite high resolution, even if it was a couple of times a day. So this was the first high resolution record of nutrient concentrations from a Greenlandic river, and it does show these very interesting diurnal changes and temporal shifts in that kind of early season meltwater. So I just wanted to put that in there as mainly as an advertisement to Clearwater Sensors, really. So next, I'm going to go on to phosphorus, and apologize for the very quick nature of this, but I just wanted to get through a few different elements before the end of the talk. So the phosphorus cycle, hugely important for life. Another big macronutrient like nitrogen. often referred to as the staff of life because of its importance in, cellular DNA, but also cell metabolism, like in ATP synthase, structural molecules like phospholipids, the backbone to cell RNA and DNA. That's why it's the staff of life. Life scavengers phosphorus. It's rare but necessary, and that's why it's often a limiting nutrient in freshwater systems. The major phosphorus compound on Earth, or mineral on Earth, is apatite. Most phosphorus comes from rock erosion on the continent, so it's a rock-derived nutrient compared to nitrogen, which is an atmosphere or atmospheric-derived nutrient. So a little bit of a contrast there. So these are the same year as the nitrogen concentration data you saw, actually, but this is just from the proglacial river. We have a dissolved phosphorus time series on the right here. SRP is soluble reactive phosphorus, which is also known as inorganic phosphorus. GOP, dissolved organic phosphorus. And on the right here is just a comparison of supraglacial meltwater. So Dave Chandler, who was camping 40 kilometers or 30 kilometers into the ice sheet interior, God bless him, was also taking samples for phosphorus. And a comparison to bulk meltwater runoff, just to show you there that we have, a diurnal, a temporal change in phosphorus concentrations that seems to be hydrologically controlled. Mainly looking at this SRP here, starts low, kind of goes high as the discharge is ramping up in Greenland. Then somehow it goes low again, then goes high again. So I was telling you earlier about the conductivity of these waters, generally going from high to low. Phosphorus is doing something completely different to the conductivity of these waters. It's going low, high, low, high. So something is different here. Something is interesting with phosphorus. And we're generally at highest discharge, ending up with our highest dissolved phosphorus concentrations. And this phosphorus is coming from the subglacial environment. There's below detection limit soluble reactive phosphorus on the ice sheet surface, that meltwater on the ice sheet surface. But we have, up to 0.3 micromolar of soluble reactive phosphorus in the ice sheet meltwaters that we're sampling at the front of the ice, those very turbid meltwaters. And they're actually very similar to large Arctic rivers. So blank spots on maps in terms of phosphorus, well, from our data set anyway, we're seeing that actually meltwater contains not insignificant amounts of dissolved soluble reactive phosphorus. Dissolved organic phosphorus concentrations are much, much lower, probably related to the amount of biological production in these glacial systems is generally quite low compared to places like the Arctic, where we have, plants developing and higher order organisms. So there we are. Soluble reactive phosphorus almost certainly sourced from geochemical weathering beneath the ice sheet. And that's that crushed bedrock interacting with that very dilute meltwater coming in from the surface. And if we look at the yields of this phosphorus, the soluble reactive phosphorus, so dissolved inorganic phosphorus, and we compare them to other areas, well, Greenland, these catchments in Greenland seem to have very high yields of soluble reactive phosphorus, up to 25 kilograms per kilometer squared, which exceeds actually most of the other values that I could find in the literature for major rivers, for the Arctic rivers, but also for other glaciers. So that's why we thought these guys were like hotspots of phosphorus mobilization, at least. Not saying anything about biological productivity downstream, but certainly from the glacial end perspective, there seems to be relatively large amounts of phosphorus being mobilized per unit area from these ice sheet catchments that we're monitoring. Because phosphorus is that rock-derived nutrient, it's mainly present in apatite. Most of the phosphorus present in these meltwaters is actually not dissolved. It's being carried by the particles that are being carried by the meltwaters, that glacial flour, suspended sediments. And we have pretty high concentrations of phosphorus in those suspended sediments. Most of that is as apatite. So these are different extractions that we do, on these sediments. And we remove the most reactive components first, using magnesium chloride and sodium hydroxide. And then we go to the less reactive components on those sediments with HCl and a persulfate digest. And apatite phosphorus is, 1,000 micrograms per gram. It's not super high. It's kind of what you would expect based on like a mean bedrock composition for phosphorus or concentration for phosphorus. But the very interesting thing with particularly these highly reactive fractions, is they seem to exchange with the dissolved pool. And to my knowledge, this hasn't really been demonstrated too many places before, but you seem to have this NaOHP, which is typically associated with iron and aluminium hydroxides, forming some kind of dynamic sync with the dissolved phase, where the dissolved phase goes high, but the NaOHP goes low. NaOHP phase goes high, and the dissolved phase goes low. So there's potentially some kind of interesting connection between the particular and the dissolved phases going on. And this is really kind of hand waving now, but I just want to show you this just to show you that like the mobilization rates of this particular phosphorus are really, really, really high from these catchments because of that high physical erosion rate. So in terms of particulate phosphorus, and this is mainly all coming from apatite in the rock, it's about 3,000 kilograms of phosphorus per kilometer squared that's being mobilized per year from Leverett Glacier. So very high amounts, really. Okay, so finally coming on to iron, which is also doing something slightly different to phosphorus, even though it's a rock-derived nutrient. I'm sure a lot of you will know this, I'd be aware of this, but iron is a micronutrient. It's needed in quite small concentrations, but it's particularly important in ocean ecosystems because iron can limit the productivity in large regions of the ocean. Not around Greenland, I should say, at least not all year round around Greenland, but definitely in parts of the Southern Ocean, Gulf of Alaska, iron is the primary limiting nutrient. And the guy who kind of discovered this, or at least popularized it, is John Martin in the late 80s, early 90s, where he came up with this iron hypothesis. And he argued back then that the inputs of iron to the ocean were one of the key controls in atmospheric CO2 concentrations and therefore climate. So he's very, very famous for standing up at a seminar, I think it was Hull, and saying, give me a half tanker of iron and I'll give you the next ice age. We've come a little bit since then, but I think it was an interesting story. Okay, so I'm going to start at the surface again, as I have done before, with some dissolved iron concentrations in surface meltwaters. So these very kind of like very pristine or pristine looking, beautiful blue color, very little stuff dissolved in there. Same with iron, really. There's not much iron dissolved in these surface meltwaters. So this is superglacial meltwater on the left. It's the log scale of iron, dissolved iron and nanomolars. These are the river waters at the front. Basically, dissolved iron is a addition of these two bars. So orders of magnitude more dissolved iron in the stuff that's coming out the front of the glacier compared to the stuff that's melting on the surface and entering the glacier. But as with all of this, hydrology, which is being driven by the surface melt, is really important for changing where the iron is coming from in the subglacial environment. So the subglacial environment here, there's some circumstantial evidence that subglacial environments might be very important in iron cycling, at least kind of in small systems that probably aren't representative of large ice sheet systems, but can give you some idea that there's some microbial iron cycling going on underneath ice sheets that might be liberating large concentrations of dissolved iron, at least in microenvironments, things like blood falls in Antarctica, and from this Christopher et al. Paper, the bottom of the ice core that was retrieved after meltwater entered the bottom of the ice core, and they re-drilled that refrozen meltwater out. But here, as I've mentioned before, we have high comminution, high rock-water ratios, redox gradients from oxic to anoxic. We know there are iron cycling microbes underneath these ice sheets, underneath Greenland, underneath Antarctica. And we know that there's large regions of the bed that are at pressure melting point that are wet. So in those proglacial river records, we see very high concentrations of iron here. Similar in some ways to phosphorus, even though the conductivity of the waters goes from high to low, for dissolved iron, which is a combination of both of these size fractions. I made it confusing here, I apologize for that, but I just want you to look at the CNFE, which is colloidal iron, which would go through a 0.45 filter. We get concentrations, in several thousands of nanomolar, and that's higher than most rivers around the world. So very high concentrations of dissolved iron. But again, like phosphorus, a lot of the story might be in the particulate phase. we do this extraction on that glacial flour that comes out in front of the glaciers and the scorbate extraction. This is targeted towards surface-bound iron 2 and also freshly precipitated 2-line ferrohydrite, which is an iron oxide hydroxide. It looks like this. It's amorphous in nature or poorly crystalline, and we know it's bioavailable for phytoplankton to a degree. It's highly reactive anyway. The concentrations on the sediments are up here. And I just plotted that next to a mean aeolian dust value that we generated from a number of sources around the globe. And they're pretty high concentrations of ferrohydrite, 1,500 micrograms per gram, 0.15 weight percent in terms of the glacial flour itself. We're also interested in the valence state of the iron, because that might pertain somewhat to the bioavailability, so how easy the iron is to access for organisms, both in situ and downstream. So we did this nanomineralogy in a synchrotron, this is diamond light source in the UK, and we're using something called scanning X-ray microscopy to look at the valence state of the nanoparticles. So here, anywhere you see kind of like lit up here is high iron concentrations, and these particles here are those that we've got spectra for here, and this can tell us something about how much iron 2 or how much iron 3 there is present in these nanoparticulate aggregates. And we kind of like sense check that against some other data from EELS spectra on a transmission electron microscope to also see very high iron 2 concentrations in a lot of these nanoparticulate aggregates. And it turns out of the ones we imaged, about 40% of the iron is present as iron 2 in those nanoparticulate aggregates. And why is that important? Well, work in the last 5 or 10 years has identified particular iron 2 as being a potentially significant source of iron to phytoplankton. For some reason, they might be able to access this iron 2, particularly if they are in iron-limiting solutions, for example. A really neat piece of work by Elizabeth Schonfeld was one of the first to show that. And she did some incubations with diatoms and fed them some particulates from different sources, and actually found that the iron from glacial material was the most bioavailable to them. And that was kind of like repeated, but in the ocean, or little microcosms in the ocean by Neil Wyatt and colleagues. And they used the same material actually that Elizabeth used in her experiment on natural phytoplankton cultures, and found that again the glacial material was the most bioavailable, that they responded to that it is to at least a degree partially bioavailable, and they can grow on the iron that's provided by it. And this is just to highlight all the other great work that's been done on iron in the ice sheet. We're not the only people, lots of other people have been working on this, and there's some really nice papers out there. Now, I should probably speed up a little bit here. This is unpublished data from the coastal environment around Antarctica. Amber Annette is responsible for this stuff on the left-hand side here. All I want to show is that a lot of this particular iron actually persists out of the fjords and onto the shelf of Greenland, and in some cases is entrained in the coastal currents around Greenland. And we're talking nanomoles of particular iron, which is quite a lot for marine ecosystems, particularly off-shelf. And this is, more than 200 kilometers from the source of that iron. And as per the glacial flour that we imaged, we've also done some work on this material that's on the coastal environment or off-shelf. And again, like very high concentrations of iron 2 in that total iron pool in these suspended particles off the coast of Greenland. And they're usually encrusted in some kind of carbon-rich matrix, but not much more there. Unpublished data, hopefully more of that to come. Iron isn't the only trace element or micronutrient that seems to be at relatively high concentrations in these subglacial meltwaters or these meltwaters coming off Greenland. Some work that we did a few years ago was published in PNAS, and a lot of the concentrations of some of these trace elements are equal or sometimes exceeding the kind of riverine mean, the non-glacial riverine mean. So these aren't non-trivial sources of a lot of different elements in the meltwater. Okay, so, sorry, that's quite a pace. Here we come to maybe what I think is kind of a trickle and treat scenario when it comes to glacial meltwaters and their contributions to the nutrient budgets, both kind of in situ and downstream environments. I wanted to talk about this study first, which I think is a really nice study from John Martin and colleagues from the University of Florida. These guys were doing some really neat work on glacial and non-glacial catchments in Greenland, and they were looking at yields and concentrations from these catchments and comparing, glacial meltwaters to what happens when you remove the glacier and you have some kind of other environment, which could be a source of fresh water as well from precipitation and snowmelt. Well, it turns out in some instances, so for nitrogen, for phosphate, for iron to a degree, the concentrations actually go down in those surface waters from glacial to non-glacial in Greenland. And the yields also go down. So this could be like a future scenario when the Greenland Ice Sheet continues to retreat. We're exposing more proglacial terrain. The system is fundamentally changing, and this could change the way that nutrients are delivered from land to ocean, or even from land to other land areas, connected land areas, or connected catchments. I'm not going to talk about this slide too much because this gets into the fjord, and I told you I wouldn't talk about the fjord, but from a nitrate and phosphate perspective anyway, it does not look like glacial meltwaters are a significant source of nitrate or phosphate when you are sampling fjord waters. And there could be all kinds of different reasons behind that I'm not going to get into, but I just want to highlight that I've talked about nitrate and phosphate, or nitrogen and phosphorus delivery from ice to ocean. At best, probably the land inputs or the purely glacial direct inputs are having a small effect on the nutrient budget in those coastal areas. And as I said, there are lots of reasons behind that I'm happy to chat about afterwards. So in my eyes anyway, we have this trickle and treat scenario with glaciers and elemental cycling, where we have these direct meltwater inputs that I've been talking about from a nitrogen, phosphorus, and iron perspective, 3 different stories. What is kind of emerging from this is that things like iron, silicon, which I didn't show, and other trace elements seem to be enriched in glacial meltwaters compared to the coastal waters. They're enriched obviously in these reactive particles, but they're relatively deplete in nitrogen species and phosphorus, or at least the phosphorus anyway is getting lost in the salinity gradient somehow. Maybe the phosphorus is going back onto the reactive particles and we're losing it from that kind of bioavailable pool. Then we have this indirect glacial meltwater input from subglacial, from meltwater-driven pumping. So this is subglacial meltwater coming in, forming a buoyant plume, which is pumping nutrient-replete intermediate and deep waters in the fjord to the surface, where they're helping to fertilize, surface productivity. So this stuff, this upwelling water induced by fresh water coming in from the glacier, is full of stuff like nitrate and phosphate, nitrogen and phosphorus, but it doesn't have much particles in. Some particles, many of the particles aggregate, fluctuate, and fall out of the plume, but it's relatively deplete in things like iron and trace elements. So we have kind of this interesting scenario where the future of ice sheet nutrient cycling and perhaps nutrient cycling in fjords around Greenland is really dependent on what happens to the glaciers in terms of, are they land terminating, are they marine terminating, how is this system likely to change? If these marine terminating glaciers that have these 2 systems of getting important elements to the surface of fjords where they can fuel biological production, if that changes, then that's going to change the amount of biological production in fjords. And there's plenty of great work being done on that by other folk. So I'm going to put it to a close there. So Greenland Ice Sheet mobilizes large quantities of labile iron, phosphorus, and silicon. I didn't talk about silicon, so I apologize for putting that in there. But the phosphorus in particular doesn't seem to be appearing in the fjord, or is lost somewhere, or is just not significant enough concentrations to make a big impact. Most elements are sourced from subglacial biogeochemical weathering, with the exception of nitrogen that I talked about. There's dissolved fluxes at the gate, so that's where the river enters the ocean, highly variable from relatively low for something like nitrogen to relatively high for something like iron. And we have this, large quantity of highly reactive labile particles that are being pumped into these marine environments, the fate of which I think is still pretty uncertain because of that kind of benthic recycling that could occur in some fjords. Okay, so with that, I just want to thank a load of people who, you know, are really instrumental in a lot of this work, from, you know, my old PhD supervisors and postdoc supervisors and mentors, people like Gemma Wadham and Martin Tranter and Leanna Benning and Rob Bracewell. Really indebted to them for getting me into a lot of this work, which I think is an interesting discipline to be in. Lots of fantastic collaborators who contributed data to what you saw in this talk. Brilliant students that I've been, you know, very lucky to work with, and funders. So thank you. I'm very happy to take questions.
Thanks, John. So if anybody has any questions, please go ahead and raise your hand. Everyone should be able to unmute themselves.
Hey, John, David Pogorski of the University of New Orleans. That was a great talk. I have a question about the size distribution of those nanoparticles. Like, does the size distribution matter, or is it really just irrelevant? They're just all just nanoparticles, and that's what matters.
It's a good question. And the answer is, I don't really know. We don't really have a good idea of the size distribution, other than kind of like some pretty pretty coarse cutoffs. So we usually filter for iron at 0.45 microns and 0.02 microns. So we know everything that's under, from, I guess, everything's from 20 to 450 nanometers in size, but we don't know what the distribution is within that size. Kind of expectation is that we're going to have kind of mostly kind of on the larger side.
Would that matter? Would those size distributions matter for any of those processes you talked about?
I mean, I would think so. Kind of biogeochemical, you would assume that the smaller particles are more reactive, have larger surface areas, more likely to be kind of amorphous or polycrystalline, because as they crystallize, they kind of coagulate and get into larger crystals, and that probably becomes less reactive and harder for microbes to access. So I would think it's very important. I just don't have any information I can share with you on that. I know that on the sediments themselves, so if you go over 0.45 microns, where we're able to image the nanoparticles a little bit easier. These things are all everywhere. They're all over the sediment, from small aggregates of a couple of 100 nanometers in size to relatively large aggregates of a micron in size. And you can see that from the synchrotron data, where we have these iron maps as well. There's all kinds of size ranges there. So yeah, I mean, and there's probably also an implication for transport as well, of the smaller particles making it further, the larger particles or larger aggregates not making it as far, particularly when you get to these marine systems and they start clumping together even more. So yeah, I would think it's really important. I just don't have any information on that. And if anyone's got any ideas on how to get that information a little bit better than I already have, then I'd love to hear them.
Yeah, I'll shoot you an email. So my colleague here has an ICP that can do single particle analysis. So basically, you can look at the distribution of size of those nanoparticles. And so, yeah, I'll shoot you an email later and copy her on there, and because she'll know the size ranges and all that. I don't know off the top of my head.
That'd be fantastic. Yeah, I've thought about single particle ICP-MS, but I have no experience with it. So it'd be great to speak to someone who does.
And you can ship samples down here for us. We got it through an NSF MRI, so it's made to be used.
Yeah, great. Thanks, David. That's
yeah,
awesome.
No problem. Talk to you later. Great talk. Thank you.
Hey, John, nice talk. Very interesting. I'm not a geologist, but I am a biologist. So I was just wondering, did you do any comparison, say the carbon to nitrogen to phosphate ratios within, say, different waters, say the supraglacial versus the bulk meltwater? Just trying to tie down where the origination, what's going on in different places. It's interesting that the iron is high because you obviously need that for nitrogen fixation, at least biologically mediated. So I'm just trying to piece together some sort of process that would provide the information that that you showed us today.
Yeah, absolutely. Yeah, great question. We have that data off the top of my head. I can't give you exact values, whether it's within Redfield or not. And I'm pretty sure it changes from surface to subglacial to fjord as well. like I mentioned, but didn't go into any detail about, is the fjord environments are generally nitrogen limited. So there's really not very much nitrogen in the fjords. A little bit of phosphorus knocking around, lots of iron. So it's certainly not an iron limited environment. On the surface of these ice sheets, there's a lot of debate that's going on. And actually, Brent Christner, who's on this call, I've seen, might be better informed than me at this stage. But there's a lot of debate going on at what the limiting nutrient is for the surface environment, because you get these amazing algal blooms that occur every summer on the surface of the Greenland Ice Sheet. And what's limiting them is kind of up for debate still, whether it's kind of light, temperature, phosphorus, I think maybe is the likely candidate for that, because there's just not much of a dust input to bring that phosphorus onto the ice sheet surface. But it's probably not nitrogen. So probably going from like a nitrogen-rich-ish ecosystem on the surface of the ice to a nitrogen-poor ecosystem in front of the ice, which is kind of interesting actually. But yeah, I mean, the ratios do exist. I would embarrass myself by trying to give you those ratios right now.
Okay, no worries. But thanks, John. Appreciate it.
Thanks, Chris.
Do we have any other questions before we wrap up today? Do the last call. Well, thanks everybody for coming, and thank you to John for giving us this great talk. We are going to continue our seminar series next week, same time, same place. Thank you, everybody.
Thanks, everyone.